All right, the final stretch of this course is obviously cosmology. We have cracked that open. We have been through a good deal of the concepts already. This chapter that you guys are working through this week is kind of just an overview of what we've already been talking about for the most part. We do introduce a few new elements, particularly the CMB, and we're also talking a little bit about elemental abundance. The goal of this week is to really answer the question, what is cosmology? And is physical science even the best tool to answer cosmological questions? Because I think there's a case to be made that cosmology was a practice for thousands of years before physical sciences got their hands on it. And actually, physical science didn't even try to mess with cosmology until about the 1960s. And so that's very interesting because most of the hard sciences that you're going to encounter have been in practice for at least a few hundred years, particularly since the Enlightenment and the rational movements that gave us the technological boom and the Industrial Revolution. So today we will go through the standard pieces of evidence one more time. Obviously, the main pieces to this puzzle, the main pillars of our standard scientific cosmology right now are the redshift, the CMB, which is the microwave background, and some discussion of the elemental abundances and how those fit into the model. Now, your textbook does a pretty good job of outlining the standard cosmology, and since we don't have a ton of time, I want to put forth some ideas about potential solutions that might wait for us in the future with respect to those. Now, last time I talked a bit about some serious issues with the interpretation of these data that are fairly well acknowledged in standard astronomy circles, and there's a lot of literature going on right now, particularly with respect to this guy. This is the James Webb, and I thought it was kind of strange that this textbook updates all the time, but it still seems to be referencing data from 2020, yeah. And obviously we've learned a lot since the James Webb has been in action. And a lot of that data is confounding in that it contradicts the models that we had presented prior to that. So, and I'll read you some interesting quotes from the literature towards the end of the discussion today, in case you don't believe me. But it looks like we are on the brink of a new model of cosmology and a new understanding of the universe as a whole. And I can't tell you for sure what that's going to look like. I don't think anyone can. But I think we can look to the past for some answers, perhaps, because oftentimes, as it is with planetary science, we have a really good idea initially, we try on lots of other ideas, and then we finally figure out how to make that original idea work. And so the next class, I'm going to explore the older ideas a bit more and see how they might fit into the future. But today, I can't look at the clock today. So somebody give me a 5-minute warning when this class is, all right, thanks, Theodore. So one thing I really want to look at is the CMB in detail. And I'll try to give you a good overview of how they came up with the idea that this microwave background was cosmic. I'm also going to present a theory that one of my friends came up with, my friend Pierre, who is a very esteemed emeritus professor. He worked for many, many years developing technology. He actually built the first 8 Tesla MRI, which I think it quadrupled the power of the MRI machine at the time, back at Ohio State in the 90s. And you might think that's a strange person to be working on something astrophysical, but it's worth pointing out that MRIs actually do the same thing that astronomers do. They look at radio signatures from the atoms in your body, and they analyze those in order to reconstruct an image of what's happening. And it's also worth pointing out that usually when paradigm shifts happen in science, they come from outside of the discipline. It's very hard to move the needle appreciably when you're working on something very detailed within a constrained environment that you've been, that you've grown up through, right? So generally speaking, what you'll find out if you go to grad school or something is, you show up to grad school thinking you're going to change the world, but in reality, you're going to work on a project that your advisor already has going in your lab. And maybe you'll move that forward a little bit if you're lucky, and you'll be able to make some advance in that field. But it's unlikely that you're going to show up to a field and completely rewrite the narrative. In fact, if you want to do that, you probably are going to have to wait until you're on your deathbed to publish that paper, because it will not work out for you otherwise. And we've seen this, right? Charles Darwin waited until he was just about dead to publish his great tome that we all now embrace. We've seen this in other fields too. This happens all the time. Of course, the Copernican revolution, that we've made our central narrative about how changes happen, right? So how we went from thinking the Earth was at the center of the universe to understanding that it revolves around the sun. Again, Copernicus carried his manuscript in his pocket his entire life. He shared it only with his close friends and got criticism from the people that he knew wouldn't impugn him. And then finally, when he was on his deathbed, he had embraced the new technology of the time. So they had something that I think was equivalent to the internet pop up in his lifetime, which was the printing press. He self-published his first book, and that ended up actually changing the world, at least changing the world in terms of astronomy and how we look at the sky. So it's very difficult to change huge ideas, and the one that we're talking about today, this standard cosmology, it's called lambda CDM, so that's cold dark matter, and lambda is, of course, the expansion constant. And so I want to present to you a sort of off-the-wall interpretation of the microwave background, which I think is really interesting. I don't know if it's the correct interpretation. I think that's really, really important. But I do think it's intriguing, and I think that the standard interpretation is crumbling like a cake. And so we do need to be looking for new ideas about what the microwave background could mean if it doesn't mean what we thought it meant all of this time, and it seems untenable at this point. So I hope that I can make it through all of that today. If not, we'll continue next time, but I do want to kind of cruise through this. And again, your textbook does a great job of filling in the blanks that I might gloss over, but I'm going to try to at least capture the salient points as we go through this. So let's talk briefly about the redshift situation. Let's talk about the elemental abundance, and then we'll talk about the C, which is cosmic microwave background radiation. And ultimately, we need to consider whether it is cosmic at all. Now, let's put this central again. Cosmology wasn't a hard science until 1964, and that was when the CMB was published. This is the first time that Lemaitre was this priest who took the relativistic equations and the interesting redshift distance relationship that Hubble had produced and spun it backwards and traced all of that expansion back to a single point. And this man, I think, would have been largely ignored, but he made friends with some of the great popularizers of the day, in particular Eddington, and he had his papers translated into English. And actually, the Pope really loved his idea, as you can imagine, because it gave a scientific context for a creation event. And there's some interesting letters, of course, where Lemaitre is writing to the Pope and telling him to put a lid on it because it's making him look bad. So this went on for 30 years or so, and the scientific community was, even Einstein himself was very, very quick to point out that there was too much religious significance associated with this interpretation. It wasn't scientific enough. So when the cosmic microwave background radiation was announced, this really started to sway people in the other direction. Now, there was a steady state hypothesis on the table at the time, and in fact, all astrophysicists had embraced this steady state idea until the CMB became part of the argument. And nobody really had a great explanation for this. So that wasn't until probably 1990-ish that most of the astrophysical community came away from this eternal conception of the universe and went over to this Big Bang model en masse. And that's really, really important to remember, because this is a pretty new idea, despite the fact that it is the only one that you'll probably hear about if you watch, Nova or Cosmos or Space Time or any of these popular science programs, or listen to Neil deGrasse Tyson or something. But one thing we need to do, and I don't want to just reiterate everything I did last time, but there's some issues with this. And one thing we need to do is look at the story that's being told. The story that's being told is dependent upon a few assumptions. One is that the distance ladder is a reasonable way to approach the map of the cosmos. And the distance ladder, of course, is this idea that the things that are very nearby us, we can assume the distances directly. We can look at parallax measurements and things that we can observe, right? But as we get beyond our own galaxy, we have to make assumptions about the bodies that we're seeing and the way that they're producing light. And so our distance estimates depend upon the properties of those bodies, which are entirely theoretical. So as we move further and further out, our errors compound and compound. And we have very little certainty about these empirical foundations that we end up processing logically. So what is logic? Well, logic is merely the ability to take some initial starting conditions, some variables, evidence, assumptions, and process it axiomatically. So if this, then that. And we trust that as long as the assumptions are good, then the output of our deductions will be good as well. And that works most of the time. It's actually the basis of mathematics, except mathematics is a particular breed of logic that's relegated exclusively to the quantitative domain. So math is just quantitative logic. But all of science tries to process assumptions in this logical fashion, and I think that that's a good way to go, as long as you remember that your initial assumptions are always subject to revision. And this is a very, very difficult thing for people in institutions to move through because, of course, the initial assumptions, the foundations, the actual bedrock upon which everything is built, if it moves, that's really bad. You have an earthquake, essentially, and you can lose the whole building, and that creates chaos, and chaos is, of course, the central crisis in being a human being, right? Every time something unexpected happens, you have to rebuild your house, and that's not easy to do. And so the initial pillars of assumption are the redshift expansion, the elemental abundances, and the CMB. Let's check those out really quickly. So the basic idea that occurred to people initially was that if there's all of these galaxies that are gripping one another gravitationally, then, and of course assuming this Big Bang idea, then there must be something that keeps them together, because obviously gravity is going to, that keeps them moving apart, because gravity is going to pull the things back together, all of the things back together. And gravity is a bit ill-defined, and I'll play with that in a minute. But from an astronomer's perspective, gravity is what holds objects together, all objects, right? And this gets us into problems because object itself is a bit ill-defined or just not defined at all. And we need to mess with that in a second. But the idea is that there's something that opposes gravity, because otherwise everything is going to just crunch back on itself, and that's not what we think we see, particularly when we consider the distance ladder as valid and we see things moving away from us, right? So what is this mysterious force that holds everything back together? Well, Einstein introduced this variable into his equation, a scaling factor that opposed gravity. And he didn't know what it meant, and he was very unhappy with it. And throughout his career, he would often speak about how this was the biggest blunder of his theory, was that it had this parameter that didn't have an explanation to it. Now, Hubble came along with his buddies and realized that, well, if the interpretation of this data is that space itself is expanding, which is, we'll deal with that in a minute, then the natural explanation for the scaling factor is that it is representative of this process. And so he seemed to believe that this was a non-issue, essentially, that yes, there is this scaling factor, but it's just a property of the universe itself, and all of that is fine. And the idea is something overall, like if we look at what we see today with the things that are far away, that are moving away faster, and if we change this, if we follow this motion backwards, if we run the movie in reverse, then we'll arrive at a point where everything started. Now, I've said this last time, but it bears repeating. This proposal seems reasonable in some sense, because of course you can reverse most very simple processes. If you are playing pool and you shoot, you make a shot, you can actually trace it backwards, right? And you can follow where it came from. This is a very simple collision. But if you take something complicated like, say, an ice cube, and you melt it and it evaporates, and then you want to try to reconstruct the ice cube from all the water molecules in the room, it's going to be very difficult. In fact, nobody could ever do that. Now, if you think an ice cube is complicated, try everything in existence and try to trace that back until whatever, right? So from my perspective, and this isn't a new revelation for me personally, I kind of thought about this when I was about 11 years old. It just seems like a very, I don't want to use the word arrogant. It seems like a very ambitious project to trace the trajectories of all of the atoms in existence back and back and back and back. And so that's what we're trying to do here with this standard cosmology, and I think this is acknowledged as kind of a strange proposal. And honestly, despite the fact that the great media channels, the great voices, the big players in this media landscape right now, you know, Neil deGrasse Tyson and so forth, there's some loud voices who are very confident in this assessment. But if you read the astrophysical literature, it's much more nuanced, right? Scientists on the ground are actually very concerned about the issues and a lot more carefully measured than the popularizers would be. And we've seen this in recent times, of course, too. If you were reading the literature during the recent pandemic, you would have realized that the narrative happening in the scientific literature was very different than the one being popularized by the media channels, particularly with respect to the ability to stop a fast mutating virus. You know, this was an untenable proposal for immunologists and virologists, but the messaging was very different at the public level. This idea that, okay, we're going to just develop this medicine that's going to stop this. And of course, we know that wasn't really possible, and it wasn't possible to the scientists at the time for the most part either, but that's what became popular. And so we have a very difficult time as human beings taking a nuanced perspective in anything, and particularly when it comes to public messaging. And so I think that's what's really happened here to some extent. But that's fine. That's how science goes. We change our minds, and we understand how things work a bit better. So continuing with the standard narrative, this explosion back at the beginning of this trajectory is called the Big Bang, of course. Now, the age of the universe turns out to be estimated directly from this, and it's essentially called Hubble time, which is an inversion of that expansion rate. So if you inverse a rate, you get a time, and that's what we have here. It's called Hubble time. The strange thing about Hubble time is it gives you a date for the beginning of the universe of about 15 billion years ago. And the assumption behind Hubble time is that the expansion rate has been continuous all along. But that's not really what we see. We actually see increased redshifts at further distance. So things appear to be accelerating, moving away even faster. And there's no easy way to make sense of that. So one thing people have introduced into this picture now to explain this process of why it's expanding is another dark concept, which is called dark energy. And you can kind of see in the history of these topics, as these dark things appear, how the believability of some of these explanations really wears off a bit because, hold on one second, because as we accumulate these holes in our understanding, at some point the entire model becomes Swiss cheese and it's not sustainable. What's up?
Is it possible that the reason that everything is accelerating is because they're getting farther and farther away from each other's gravitational pull, and thus there's less resistance?
It is possible. It is possible. Of course, this conclusion, like the rest, depends upon the idea that the distance ladder is in fact reliable and that the redshifts are due to true recession velocity and not due to something else. Because one thing that's quite interesting, of course, and I was going to get to this later, but I think it's a good time, is that reddening of light is also easily interpreted as light losing momentum, right? Now, nobody has successfully, well, there's not been an accepted explanation for how light could lose its momentum in a way that didn't involve scattering. And I think a lot of this problem comes down to us not having a physical explanation for light. Because right now we treat light as if it's just this ball of magic that travels between one atom and the next. And I don't think that that's reasonable. I think that we are going to have to come up with a physical explanation for light. And there's a lot of cool work going on with that. I'm going to propose something to you in just a second. So dark energy. Dark energy. Now, what is dark energy? Well, one possible explanation is this dark energy reveals something important about the cosmological constant. Maybe it is, like Quentin says, it is some engagement of gravity at this point that holds things back. But again, there's a force that opposes that gravity, Quentin. There's something that is actually causing it to expand faster, right? So gravity is not doing what we would expect it to do and hold these things together. And that's the concept, where the concept of dark energy, there's something pushing, opposing gravity actually that's doing this. Now, there's a concept that goes along with dark energy, which is the vacuum energy too. There appears to be some slight fluctuations in between atoms, actually. There's an immeasurable amount of energy, it's actually quite significant, that hovers around some 0 points. So something is being displaced, something is being displaced in the opposite direction. It hovers around 0, and this is often referred to as 0-point energy. But there appears to be something vibrant in between atoms. And honestly, that makes a lot of sense as we work our way towards a physical mechanism of light. Now, you might ask yourself, why don't we have a physical mechanism of light? And actually, prior to the early 20th century, it was assumed that there was a medium which light played out in, right? Just like sound waves or any other waves, ocean waves, a wave is really a verb. It's really what something does. And so the question is, what is doing light? Now, the search for that medium was completely fruitless. There was a great deal of experimentation in the early 20th century, in the late 20th century, early 20th century, I always get these messed up, late 1800s, early 1900s. There was a great deal of experimentation. But the experimentation made an assumption about the medium, which I think was deadly. They assumed that the medium was distinct from the atoms itself. And what does that mean? Well, they set up all of these experiments that assumed that if you had a medium, that as atoms moved through the medium, there would be a drag, right? So if you sent light out through the medium, there would be some retardation, some lethargy as it returned, right? But nobody, for some reason, considered that the substance that spanned the distance between atoms was the same substance that comprised the atoms themselves. And I think this is where the future is headed, actually. And it's not my idea alone, although I'm a big champion of this idea, but there are some very, very notable mathematicians and astrophysicists that are working on this. In particular, my good friend and emeritus professor from Caltech named Carver Mead. And Carver has done a great historical analysis and pointed out that G.N. Lewis, who gave us our chemical bonding arrangement, you might know him from Lewis bonding and things like this, great chemist, actually pointed out that there was no reason to believe that light could ever occur without two atoms. It had to be a handshake between two atoms. And so the question naturally becomes, how are they shaking hands across the void? Well, one possibility to that, one that I champion a great deal in my own time, is the idea that stems from our quantum picture of the atom. See, we have these shapes, perhaps you've seen them, the shapes of the atomic orbitals, right? How do we derive these? Well, they're fundamentally derived as harmonic overtones, excitements of the shell of the atom, which we refer to as the electron when it's in motion, the electron shell of the atom. And what's really interesting about the wave function, which is what tells us the shape of the atom, the wave function for the electron, most of the charge is found very close to the nucleus, as you might expect. Of course, the charge goes down right at the nucleus because that's where the proton, the opposite charge, is located. But actually, the electron wave function extends infinitely. And of course, infinities are troublesome, but it does tell us something quite interesting, which is that the shell of the atom does seem to extend to great distances, although it's very thinned out at that point. You're very unlikely to make a measurement of it at a great distance. You're much more likely to have your measurement be found at an early distance. And so one way I've begun to think about the atom is that it's not just this little blob, a little bubble that's isolated. It actually has little thinned portions that extend very, very distantly in all directions. It almost has this radiation to it. It has a radiative shape. And so this is an interesting picture of the atom if you give it these radiations, because they're consistent with the quantum mechanical models, and they actually allow you a way to connect your atoms to one another, at least connect the atoms to the ones that are next to it. Now, if you couple that to a relay system of light, where light, of course, is not just traveling from 14 billion years to us, but it's actually going from one atom to the next across that span. Well, then you have maybe the possibility of understanding what this vacuum energy is. It's actually the motion of those individual pieces of the atom that are in between. Because what does energy mean? We've talked about this a long time ago. There's no real rational definition for energy other than something moving. Now you might say, well, what about potential energy? And again, if you have a spring that's tightened up, well, it has the potential to go into motion, right? It has the potential to supply energy. And so if energy is just the motion of stuff, then something has got to be moving. And I think that's worth considering as we go forward. So your textbook, it goes on and talks about this expansion business for a while. And it gives this idea, of course, which we've seen before, that the scale is changing, right? The actual distances are changing. Well, it's quite obvious if you assume the distance ladder that the distances are changing, but it doesn't make for much of an explanation in my book, right? Because space is just a coordinate system of locations. But if the coordinate system of locations is changing, why is it changing? Why are the things moving apart? Why do things move in the presence? Why does the Earth move around the sun, right? Well, to say that it moves around the sun because the distances are changing is not satisfying to me personally. I'll let you make up your own mind about that. So, the standard explanation that is sort of wilting on the vine right now is the idea that redshift is simply this idea that space, being an elastic concept, is opening, and so the wavelengths are opening as it goes. But of course, elasticity is a property of materials, not a property of ideas like space-time. And so applying physical processes to ideas is a very nefarious activity in physics. And I think this has gotten us into a great deal of trouble lately. Of course, we know, I spoke last time about how bass frequencies are usually the perceptible ones at distances. And a lot of this has to do with friction losses across distance. As a wave travels through a medium, there's a great deal of friction as those molecules inside of the table or whatever are crashing into each other. They vibrate the atoms a little bit. There's some friction losses. And so if we have a material model of light, this is why I think it's so important to even bring it up. If we have a material model of light, then all of a sudden we have the ability to introduce some analog of friction into our conception. And we have a way to understand redshift that doesn't necessarily involve the warping of ideas. We can actually talk about material representations of what cause material effects, which I think is extremely important. Now, let's look at the different models that were available to the cosmologists. Of course, this all occurred in the last 50 years, and these different models were tried on. Of course, in this graph here, we have time as the vertical direction. Now, the first two potential universes that the cosmologists considered are ones in which the rate of expansion actually slows down over time. And then the one on the left eventually slows so much that it stops and perhaps reverses, and you end up with this thing called a big crunch. And the one next to it keeps going, expands forever, but it slows down as time passes. And this coasting universe, as it's called, is one where the expansion rate basically stays the same, and it keeps going and going. And then, of course, the accelerating universe on the right continues to expand faster and faster forever and ever. Now, in a universe with dark energy, which is the one that's proposed right now, the rate of expansion increases with time, and then the dark energy takes over after gravity is out of the way, like you were saying, and then the expansion goes up and up and up forever. Now, because this cosmology, as you might have noticed, it's a very apocalyptic cosmology, actually, which I wonder if that in some sense reflects our own spiritual, I'm sorry to use that word, our own psychological, synonymous with spiritual, our own psychological state as a people on Earth right now, to some extent, Think about the last movie that you saw about the future. Was it a utopian picture, or was there a lot of stuff on fire? You've seen some utopian pictures? Name one. Yeah. So we tend to think about the future already as a culture. We tend to think about it as falling apart, which is, I actually think that's more than a little disturbing. But I think that it makes sense that the cosmology that we've been championing in the last 50 years also reflects this idea that things will fall apart. And I don't think that scientists are ever really capable of being perfectly objective. We're human beings, and we view the world through human eyeballs. So we have this cataclysmic view of what our evidence means at this point. There's a couple more features to this which are going to lead us to the CMB. There's three basic ideas here. One is that as the universe cools, that the universe cools as it expands, right? Again, the heat death of the universe, everything is tending towards this dead state. Well, if the universe is expanding, then it should cool, fair enough. Perfectly logical. The second idea is that at the very early days of the universe, it was extremely hot. This is just working backwards, fair enough. And because it was so hot, it was too hot for atoms to exist. And so the idea is that because there was no atoms, there was only light. Well, this is extremely biblical, right? In the beginning, there was light, so fair enough. But this begs the question of what light is once again. And there's very little reason to believe that there's such a thing as light without atoms, right? In fact, there's no evidence that you can have light without atoms. So this one gets me I'm a little skeptical of this assumption. And then the next idea is that the hotter the universe was, the more energetic that light was, and there was more possibility for this light to produce these interesting matter-antimatter reactions. Now, I don't really have time to go into antimatter and matter with you today, unfortunately. If anybody wants to talk about it, though, I'd be more than happy to give you my thoughts about it. But it really, really comes down to the idea of understanding what's happening when we call something matter, and what happens when we call something antimatter, and what sort of observations we're using to make these conclusions. What is a particle, right? Well, a particle is an event, actually. It's not necessarily a body, like an atom or like a table, right? It's a particular energetic event. It's some sort of result of an electromagnetic detection. And essentially what we note when we say that we've observed some event of antimatter occurring, is that it has a very opposite energy, a different vector of motion than what we would standardly call a traditional piece, right? Like an electron has a particular momentum to it. It turns in a particular direction. And I've given you my interpretation of what I think the atom's doing during the electron's motion. I think that the surface of the atom is moving in a particular way that allows it to engage in this electronic fashion with other atoms. So antimatter would just be the opposite motion detected, right? Okay. There's a few pieces of information that are interesting that are used to defend the standard cosmology, which concern the elemental abundances. For instance, the amount of helium that we see in the universe doesn't seem to be appropriate for the number of stars that we imagine are out there. So we've talked at the beginning of this course about how helium is produced through fusion. It doesn't seem like there's been enough stars in this length of time, in this 14-ish billions of years, since this Big Bang event to produce all of that helium. However, the lambda CDM model touts that it's able to explain this due to these particular recombination events that happened within the first few moments of the universe. And this is all well and good, but there's other elements that actually contradict that. The lithium abundance. Lithium is also one of these problematic substances. There's not enough stars to make it. Well, the predictions that are used to give us this triumph of helium also give us the wrong value for lithium, which is off by about 3 or 4 times what it should be. And so I'm not sure this is quite the touchdown that it's treated in your textbook. All right, so let's talk about the temperature, because the basic principles tell us that the universe was much denser, it was much hotter, cooled as it expands. This is kind of like if you have a can of spray paint or something, and you're tagging up a wall and it gets really, oh, you would never do that. No. And it gets cooler as you feel it cool down, right? And the idea is that this idea was actually proposed long before the CMB was discovered, was that, oh, we should be able to see some trace of this as it happens. And this is essentially the proposal that leads to the CMB. And this is actually by far and away hailed as the greatest triumph of the lambda CDM model, is that, hey, we knew we were going to see this, and we did. The interesting thing, though, is that the proposal for a source of light at the beginning is fine, because of course, as the atoms when they're, at least, let's say, when the atoms first appeared, well, of course, they have very energetic, there's going to be a lot of light, fair enough. But nobody thought that light would be in the form of black body radiation. Why? Because gases don't give off black body radiation, ever. Under any circumstances has anyone ever been able to take a gas and make a black body spectrum from it. Of course, the gas in these lights, if we were to hold up a prism to these, you would see very, very nice lines, green, blue, and red lines coming from this light above your head, because gases have only a few degrees of freedom, right? I want to go over this because it's extremely important. And this is why that I was so fixated on the composition of the sun in the first couple of weeks. Again, we treat the sun as if it is made of this burning ball of gaseous plasma. But this is also a somewhat untenable proposal because you can't make a black body spectrum, a continuous rainbow of color from a gas under any conditions. And of course, the way that this is rescued is that there's some sort of, the photons get trapped inside the sun for millions of years and they just happen to be emitted at the perfect density, at the perfect power densities to give you this black body spectrum. Of course, no one's ever been able to actually show that that's possible on Earth. They just point to the stars and say, well, the stars do it. But do they? Or are the stars actually some sort of condensate? Are they actually more like a metal, more like a liquid of some sort? Well, they certainly look like it on the outside, for one. But at any rate, the proposal that was put forth was that once we saw something like this microwave background, well, that's it. That's got to be this hiss from this Big Bang event, which we have been suspecting was the case since we came up with this Hubble distance relationship. But Kirchhoff, the guy who did all of the work on the black body business, was long dead by that point, and there was very few people to stand up and say that gases couldn't actually accomplish this. So the idea was that, well, let's leave this alone for a second. These two gentlemen were actually working at Bell Labs out on the East Coast, Penzias and Wilson. They were actually trying to make some detailed observations of a supernova. And they had this problem with noise in their antenna, and they couldn't get it to go away. And they realized that it was a black body noise, actually, which was really interesting to them. And the proposals on the table were, of course, that the temperature of this hiss would be appreciably lower than it was, obviously, in the deep past, since it's been eons since then. And actually, people imagined that it would be, something like 1,000 times less the temperature of this signal. And Penzias and Wilson's black body background turned out to be in that ballpark. So people were imagining that it would be, maybe 40 Kelvin, but Penzias and Wilson's hiss was about 3 Kelvin. People repeated this, and they found this hiss over the years is about 2.73 K. It's often called the 3-degree microwave background. Now, that's very, very cold, by the way. Remember, absolute zero means that the atoms aren't even moving. We can't really produce absolute zero in a laboratory. You can't make an atom stop. But it's very, very cold. And the signal was very, very clear, actually. That was one of the most perplexing things about it. Now, think about this. When we go and we make measurements, when we make these measurements about, say, the speed of stars, we've talked about recession velocities, we've talked about angular velocity of stars being used to calculate these Doppler shifts and so forth. The errors on these measurements are at best 10%, usually worse than that, 50% sometimes. The error bars on this microwave background radiation were almost non-existent. It was as if you were taking a picture of a glowing hot ember inside of a fire. It was absolutely pristine. And honestly, that's a little weird by itself, because if you're talking about something that's coming from very far away, you would expect it to have some error on it, because surely there's other things that are getting in the way. But not the CMB. It was absolutely perfect. Now, they started sending some balloons up into the sky to make measurements of it. Well, maybe we need to rule out Earth-based radio signals and so forth. And the error bars went down a bit, particularly in the lower end of the regime. Actually, you'll never see the lower end reported in the literature. It's kind of ignored because it's such a mess. But more or less, it had pretty well replicated curve to it. And as time went on, the astronomers built better and better satellites to measure this. And they ended up actually sending a device out to quite far away. They centered, we'll talk about where that was located in a minute. But there's some issues with that. So the main satellite that we generally base our measurements of the CMB on was, well, there was two of them. One was called COBE, and the other one was called Planck, and they were very, very similar builds. And they were, in fact, measuring directly this radio signature. And you can see, actually, the COBE version was more or less isotropic, going with the cosmological principle. It's the same in all directions. The next, the Planck one was actually next. And the Planck one was a little bit more spotty, but on average, it balanced out, more or less. Later, we sent this satellite out to L2. This is quite a ways away from the Earth. And we got the picture down here that everybody's familiar with. Now, we'll return to that one in just a second. But there's, I guess it's worth pointing out that the picture that you see here, and I talked about this a bit last time, but I want to reiterate it, it didn't actually measure the radio signal directly. It took the signal that they had measured near the Earth, and it went looking for that exact same signal. And what it did was it had two horns on it, two antennas, essentially. It looked behind and it looked forward. So it compared the difference between the forward measurement and the back at the black body temperature and spectrum that it expected from the COBE project and from the land-based measurements. So it wasn't a direct measurement, actually, itself. It knew what it was looking for, and it compared the amount of that signal in the front versus the back. And so what you have is actually a differential heat map that results from it. And actually, that differential heat map by itself warrants a little bit of skepticism, too, because what it actually looked like originally was something like this. And that's the galaxy, of course, that you see, which is an extraordinary source of microwave radiation. So they made some estimates of where the stars were that were emitting all of that noisy stuff, and they deleted it, and they get something that looks like this, which is, of course, equally troubling because now we have these great bands of hot and cold. Well, they removed those as well because, of course, those were probably due to our motion. They were a Doppler effect. And actually, that gave us the model that you see above. And here's a quote from the original paper, by the way. The data will be calibrated to the temperature differences on the sky by comparing the raw output to the signal expected from the known dipole, which is the one, of course, we measure here on Earth, and the one that's measured in the sky right above us with the COBE project. So there's been a lot of manipulation of this data, and I don't think that it's I don't think that it's funny business so much as it's processing our assumptions, right? So the assumptions are now baked into this picture that we have, which is no doubt making for a lot of headaches now, particularly because what we've discovered very recently, and I mean like this year, is that the motion, this Doppler motion, let me go back to it really quick. This Doppler motion that we subtracted, it actually turns out that the motion of the CMB and this Doppler motion with respect to redshifts aren't commensurate with one another. They're in different directions. And so the CMB appears to be moving differently than us, which is very strange if things are supposed to be expanding away from one another. And so people are having to revisit the idea that maybe this subtraction wasn't fair. And I'll read you some quotes so you don't have to take my word for it later. But the idea is that that ascribing a cosmic source to this might have been a bit hasty. Now, by the way, this is where the WMAP satellite was located, the one that did the differential measurements. It's at L2, which is a place that's shadowed, right? It's on the back side of us, so it's, of course, away. And, you know, this would have been a good experiment if it would have actually tried to measure the CMB directly, but it didn't. And I'm very curious why it didn't, why they didn't have a monopole measurement, which would be the direct measurement of the CMB, but instead it was a direct one. And I suspect that's because it wouldn't have looked very pretty. Now, there's something else here. I'm going to kind of move towards, so if the CMB isn't cosmic, if it's just the MB, the microwave background. Well, then what the heck is it? Because it's a beautiful black body spectrum. So what could make a black body spectrum? One thing that's very interesting is that ground-based communication satellites calibrate their antennas on the CMB, and this is quite interesting. But you might ask, what do they focus on when they do their CMB calibrations? Well, it turns out, for some bizarre reason, they point their satellites at the edge of the Earth when they do their CMB measurements. This is a standard process for all of those gazillions of satellites that are out there floating around, providing us with cell phones and all of our communications technology, right? They actually point at the limb of the Earth when they get that, because that's where these guys aren't scientists, they're just trying to calibrate their antennas, and they're like, this is a standard that we can use. Well, they just happened to realize that the strongest source of this microwave background was actually the limb of the Earth itself. And limb, by the way, just means the edge, right? When we talk about the limb of the sun, we talk about the very edge of the sun. So for some reason, the CMB for these folks, these technologists, is most visible to them at the very edge of the Earth. And this is puzzling. And I think that this can lead us into some assessment. Well, I'll just leave this up, and you can check it out later if you, we'll put it on YouTube. All right. Now, the designer, yes?
When you say edge of the Earth, do you mean the atmospheric edge or the edge of like the mountains and the oceans?
It's actually, it's a position between it's the visible edge of the Earth, yeah. Now, the atmosphere, it's a good question because, well, I'm going to start talking about water here in a second, which is really interesting. Because water was a real nightmare for for the people who were designing these first CMB detectors, right? And actually for Penzias and Wilson, they were constantly plagued by water presence, particularly condensed water inside of their horn. This was a real problem for them. I'll read you this quote. This is from one of the people who worked on one of these original satellites. Temperature, pressure, and constituent inhomogeneities occur and, in fact, are the largest source of random noise in ground-based experiments. However, they do not contribute to systematic errors unless the particular observing site is anisotropic in a gross manner because of a large lake or the ocean in the direction of the zenith scan, for instance. The atmosphere and the CBR, that's the CMB, contributions are separable in this case without further measurements or modeling. Now, Penzias and Wilson, who discovered this originally, their satellite was actually right there on the Atlantic coast in New Jersey, in Homedale, New Jersey. It was actually about a mile away from the ocean itself. Now, of course, they were able to subtract atmospheric interactions because the strongest radio signal that water gives, and it's a very strong radio absorber. Perhaps you've noticed this if you've been in a storm and tried to use your cell phone. It's actually quite a good interferer. But atmospheric molecular water, it absorbs in a particular span which is separable from the CMB. So nobody was concerned that the CMB was being contaminated by molecular water, that is atmospheric water. However, nobody seems to have considered the idea that actually water has another kind of vibrational mode. That's its lattice mode, right? That's its hydrogen bonding. So inside of water, water is an amazing molecule. I did my PhD studying strange behaviors of water in lattice structures. And water can form incredible structures, actually. Because of its hydrogen bonding, it can bear extraordinary tensions. Water can behave in a very much like a structure, like a body, right? And it turns out that the temperature of the hydrogen bonding lattice inside of water, that's to say, under great pressures, in theory, is absolutely commensurate with the absorption band of this. And of course, liquids, we know, do give off black body spectrums. And so some suspicion has turned towards the actual oceans themselves. Now, this is an interesting proposal because you might say, why not just point the antenna at the ocean and measure it? Well, that's one thing that you can do. But one thing that's interesting is that, I'll come back to this in a second. one thing that's interesting is if you look at the way that the lattice bonding in water emits radiation, what you find is that it's extremely susceptible to polarization. That means the angle at which you view it. Now what happens is if you point your antenna directly at water, you'll see that the temperature of it goes up, and there's a perfect place to measure the temperature of the water from above. If you measure the radio temperature of the water from above, you'll of course get the temperature we're all familiar with of water. In other words, the oceans are about, let's say, hovering around, just above freezing on average or something, right? Maybe a bit more. They're cool, but they're not frozen. Okay, so you get this temperature. But what happens is if you turn your antenna away from the source a little bit, the temperature goes down appreciably, actually to the point that at its limbs, at the limbs of the horns that you're measuring with, the H bonding temperature approaches something close to what we measure with the CMB. Now, you might say this is preposterous, that water could be could actually accomplish this. There's another piece of evidence that's really quite interesting too, which is nuclear bomb tests. So one thing that people noticed when they were doing these tests on nuclear bombs was quite interesting, which was that when water was shock loaded, it lost its transparency, actually. There's a ring of blackness that happened as the lattice, the water lattice, compressed. It actually went from being opaque in lower frequencies to being opaque in the visible range. You couldn't see through water when it was compressed. And this is a very interesting piece of evidence because what it tells us is that the lattice of the water, the way that it's actually networked with one another, when that lattice changes, it changes the optical properties, the ability for it to absorb and emit light. Now you have to imagine that the oceans themselves are actually under a great deal of pressure, and there's the potential for all sorts of interesting lattice arrangements in such a situation. Okay, now I guess one last piece of this puzzle that I should point out is that when people were doing black body studies, Kirchhoff, we talked about it at the beginning of the semester, what did they use? Well, they used soot as the ideal black body. And what's interesting about soot and about carbon is that it arranges itself into this beautiful hexagonal lattice. The same lattice that water forms under great pressure as well is a hexagonal structure. So ideally, water's H-bonding network would have a beautiful black body spectrum. Where are we at on time? That's fine, yeah. I'm just trying to keep tabs on it. So at any rate, this is an interesting proposal that my friend Pierre has kind of dedicated his life to at this point. And I don't know if he's right about that, but it is certainly interesting. I don't think that the cosmic origins of the microwave background are going to be able to be a sustained proposal for too much longer. Of course, one easy way that we could test this hypothesis is to simply send something like COBE out to L2 and see if we actually do measure a microwave background. That's not just a differential measurement, but it is a direct measurement. Unfortunately, I don't think that anybody is actually planning on doing that. Now, I just saw this article when I was scrolling through the PopSci stuff the other morning. I usually take about 5 minutes to look through the PopSci headlines. And there was a new headline that caught my eye yesterday. And it was from Quanta magazine. And this was a quote from a Max Planck researcher who's working on a new assessment. And he says, "The CMB was the key piece of evidence that helped establish the standard model of cosmology. This paradigm really survived the test of precision measurements until recently." This is Aikiro Komatsu, a cosmologist at the Max Planck Institute for Astrophysics. And he was one of the original members of the WMAP team. He says, "We may be at the crossroads of a new model of the universe." And I think this is really, really exciting because I don't think that people who take this course 50 years from now will have the same experience that you guys have taking this course, because I think we will have a new model and the textbooks will just read, and maybe that will be, in some sense, satisfying because whoever's teaching this class then will have the ability to sit here and read from the textbook and have some confidence in it. I think that will be really good in some sense, but I don't think that they'll have the really magnificent experience of seeing science unfold in real time, particularly a paradigm shift as big as Darwin or as big as the Copernican revolution, which is actually happening right now in real time. And so this brings us to what I really want to get into and pull apart for you next time, which is the proposal that was on the table before the standard cosmology today, which was an eternal universe. A universe that doesn't end in a heat death, an eternal universe that continues as it always has. And I think that there's a great deal of comfort in such a model, and I would like to get into why I think that and why the ancients thought that to some extent. You know, Quentin, you mentioned last time this idea that in an eternal universe that perhaps, you know, maybe you can put it in your own words, but you said something about things happening over again, perhaps, that had already happened before. That the idea that, go ahead.
I don't think I remember mentioning that. Sorry, excuse me. I do remember a theory that once the Big Bang has exhausted its momentum, that it will eventually collapse back together again. There's a theory that the universe just will repeat itself, and that we'll have this class over and over again.
Yeah. So I think it's an interesting idea, and I think that the eternal universe actually houses this idea too. So Nietzsche proposed this really interesting paradigm where he said, of course, in Nietzsche's day, everybody thought the universe was eternal. And Nietzsche said, given eternity, all possibilities will eventually be exhausted. And so if you wait long enough, and I don't know that I agree with this. Actually, my wife and I argue about this all the time. But if you have all possible states of matter and all of their configurations, and you go through that, and you go through that, and you go through that. Of course, eternity is a very difficult thing for us to put in our heads. But it seems possible that you come to a point where you have to start over, and you have to start repeating those confirmations. And I think there's a really interesting metaphysical puzzle there, and Nietzsche called it the eternal recurrence. And this is the idea that you would be happening again in a gazillion years from now because there's only so many ways things can unfold, and eventually you'll make it through all of those. And so there's something really interesting there because as opposed to a heat death cosmology, the idea is that is something closer to the Eastern cosmology, which I'm going to really get into the details about next time, which suggests that there's actually a cyclic nature to the universe, where things actually occur, they occur again, and they occur again, and this happens forever. Yes?
I remember reading a long time ago something about how it might be like the second or third or fourth 10,000th cycle of the universe. What are your thoughts on that?
Yeah, I think that it's really interesting. This is the question. The question you have to really ask yourself is, will the universe ever run out of possibilities? Let's just for a moment assume that the Big Bang turns out to be not the case and that the place has always been here and it always will be here. I don't know if I can answer that for you, but you have to ask yourself whether possibilities are endless, whether a life could happen twice. It's a very interesting question. I mean, there's, of course, twin studies are actually a really interesting phenomenon. So people look at twins who are separated at birth. And of course, these people have identical genetic compositions, right? And oftentimes they had identical births. They had identical times maturing inside of their mother, right? So ostensibly, they're very similar productions physically. But oftentimes, twins are completely different, which is very bizarre. Now, oftentimes they aren't, which is even more bizarre. So you'll find people who are reunited 40 years later, and they're both firemen with mustaches who drive old refurbished Ford Mustangs, right? This happens a lot, actually. And so I think the jury is still out. I think we don't really know. I tend to think that, personally, I tend to think that things don't occur the same way twice. But maybe that's just because I can't imagine eternity. I mean, we're not talking about a long time here. We're talking about an infinite amount of time. We're talking about however much time you can imagine, a little bit more than that, and then a little bit more than that, right? Now, of course, the beauty of an eternal cosmology is that it actually allows us to solve a ton of these darkness problems in our astrophysics as well, because now we have a tremendous amount of time to produce cold things, right? It also helps us perhaps to understand why we don't see more people out there when we look at the stars. Because if it's been a really, really long time, then perhaps there has been a great deal of other civilizations. Perhaps there have been all sorts of humans in our galaxy. I don't know about humans, but thinkers like us who have explored the stars. But perhaps they happened trillions of years ago, right? So the timetables that we have been problematic throughout this course. They've left us with things like black holes, dark matter, dark energy, right? They've really put the mystic back into science in a way that I'm deeply uncomfortable with. Because I think that there's two different ways to look at the universe that are equally real. The one is, of course, the physical representations. And ultimately, all we can ever hope for in our quest for understanding is maps. Science gives us maps. Theories are maps. They tell us what to expect when we look out on the world. But there's a different kind of map as well that's equally valid, and our culture hasn't really put our endorsement upon those, and those are the mythological maps. Those are the maps that tell us about how human interactions go on Earth and how we should behave if we want things to work out for us. That's a very valid way of looking at the world. In fact, there's an argument to be made that that's actually a more valid way than the physical representations, because those maps can actually tell us how to get to a future that doesn't look like the ones that we draw in Hollywood right now. And so, you know, we have two eyes for a reason, right? If you have one eye, you have no depth perception. You have another eye so that you can triangulate it. And so I think that cosmology deserves two eyes as well. One which is physical and doesn't involve mysticism and doesn't involve breaking physics. It involves simple material explanations for a phenomenon. And then there's another eye that we have which tells us how we actually behave in the world, which tells us stories of what happens when things go the way that they go, when you're cast into this chaos, right? It's a story we tell without realizing it. I was up in Portland last weekend hanging out with a friend, and my friend is a very famous animator. He's working on this huge multi-million-dollar project right now, doing stop-motion animation for a film that's coming out right now. Well, actually, it's not going to be done probably for a couple more years. But the central feature of the film, and this is based on a novel by, you guys know the band The Decemberists? They wrote this. Oh, yeah. So him and his wife, they wrote this book, and it's being adapted into a film. And the central feature of this film is that the characters are, there's this impenetrable forest on the edge of town. And when they go into the forest, they face all of their trauma from earlier in their lives, right? And I was talking with my friend Nelson about this, and I was like, man, this is crazy. This is the slaying the dragon in the forest story. This is the oldest story of time. And he was like, wow, man, I never thought about that. And it's wild because people, they make these representations without realizing that they're actually happening. That's freaking crazy. So you have this knowledge base that's inside of you. It's been there in the stars. People have been telling stories of these wrestling with chaos forever. And we don't even realize we're doing it. There's this knowledge base that we have that we don't even know that we have. And so what I really want to close down this course with on Thursday is the proposal that there's two good houses for cosmology. And only one of them is in physics. And the one that's in physics has tried to subsume the other one, and I think that's a bit to the detriment. Because what I'm trying to do here is I'm not trying to tell you that the physicists are morons. I'm trying to tell you that they're trying to do a job that isn't their job to do. It's actually the job of the artists and the myth makers, right? And so our ability to separate those things out, I think, is going to allow us to produce a vision for our future which doesn't end in ashes, which is something we desperately need right now. Because every civilization that's ever existed on the earth has gone that way, right? And we don't want to go that way. And the only way we're not going to go that way is if we imagine a different myth for our future that doesn't involve this heat death and this idea that our only destiny is one that ends in death as a civilization. All right, let's stop there, and we'll pick up on Thursday. Have a good week.